Hello, everyone, and welcome to Rational Science. I have a few things to say. The first one is that next Sunday we're going to be off for the holidays. Okay, so I'll see you back again next Wednesday. And next Wednesday we're going to do a wrap up of the year, and as well I'm going to open up the floor for any questions or comments. So we're going to be doing real time questions and answers. Get your questions ready if you want to bombard me. Okay, so that's going to be next Wednesday. Okay, next to the last day of the year. Okay, what do we have today? Well, today we're going to be looking at the history of chambers. Okay, because see, they use these cloud and bubble chambers and other types of chambers to detect particles. Okay, and so we got to look at to see if that's a valid procedure to determine what you're staring at is a particle or something else. Maybe it's a ghost or a spirit. Who knows? So let's find out what it is. Okay, to get the ball rolling, we got to start with this gentleman. A good place to start, Joseph Thomson. And why do I start with him? Well, in 1897, he allegedly discovered the electron bead. In fact, it went a little further because he discovered that it was part of the atom, something that was missing from other researchers, that conclusion. And that meant that you could break up the atom. The atom was made of parts, and now you could, separate them, perhaps. And so this is what was in the minds of a lot of the mathematicians in those days. And so you could say that's when the subatomic particle world started. Okay, and what they're going to do for the next more than 100 years, right, is look for those particles. Okay, and that's how the chambers came into being. Now, it's important to note, I thought it was very interesting to note at the time, that there was also a study of mass of the electron. Okay, and here's this unsung hero, and his name is Walter Kaufmann, and he apparently was the first guy to prove, okay, that mass is velocity dependent. Okay, are we talking about mass, or are we talking about something else? Are we talking about weight? Okay, because what do you mean it's velocity dependent? I thought mass was quantity of matter. Quantity of matter, you just count atoms, or whatever unit of mass you've got. Let's call it X. So we count number of X's. We got 1 billion X's, and that's what makes up a table. We're done. Okay, that's the mass of the table, quantity of matter, or a measure of a quantity of matter. But when you start accelerating the table, or the elephant, or whatever, are you talking about mass, or are you talking about the pressure it causes on the scale? Okay, so these are two different notions. One is the quantity of matter, the other one is acceleration and pressure. And so these people say, like you've got here, confirmed for the first time the velocity dependence of the electromagnetic mass, later called relativistic mass of the electron. Okay, so these are important developments because not only are they showing that electron is part of the atom, it's a tiny bead that's going around there, they realize it had very little mass. This guy determines that, the electron has some mass, and again, what are we talking about? We're talking about what the electron is made out of. To this day, it's considered to be a particle, an indivisible particle. In other words, a particle that has no parts to it. Okay, and so the question is whether this is mass or weight. Okay, and again, if you're going to use Einstein's equation, you might as well replace the little m with W because it's weight that they're talking about and not mass. They're not talking about quantity of matter. And what they do, they take the c squared, put it on the other side. In other words, E over c squared, and that's equal to mass. In other words, what they're saying is energy, which is a dynamic phenomenon, right, divided by c squared, which is a trajectory, an itinerary. I put the word orbit. In other words, there are two verbs. And you divide one verb divided by another verb, and you get a noun. You get phenomenon divided by orbit, and you get elephant. What the hell is that? But that's what they're doing. That's how they're calculating the masses of all these subatomic particles. And again, are we talking about quantity of matter or what the ball weighs on the scale? In other words, are we talking about counting units of mass, components, or are we talking about how much pressure it causes, for example, on a scale? Okay, so those calculations of energy converted into mass, that's weight. That's not quantity of matter. Okay? And yeah, they like to say it's a measure of a quantity of matter to soften the blow. No, what they're doing is they're doing weight, and they're calling it mass. No one has ever done anything other than weight here on Earth in the last 10,000 years that we've been dealing with mass and weight. Okay, but the one key guy that comes up is this guy, Charles Wilson. And you can see I circled him there. He's part of the group that belonged to Joe Thomson. Okay, these were the Cambridge boys. I think this picture, one of those is like 1898, end of the 19th century. Good old boys. Okay. And but Charles Wilson, even though he was a so-called physicist, he was a mathematical physicist, he dedicated his life to weather. He was a weatherman. Okay, and that's why he's going to develop the first chamber known as the cloud chamber. And here's a picture of his cloud chamber. Okay, sealed environment containing a supersaturated vapor of water or alcohol. I like the alcohol part, really. When a charged particle interacts with a mixture, it ionizes it. The resulting ions act as condensation nuclei, around which a mist will form or a trail will be left. Okay, so what are they talking about? Well, here's a picture of what they're talking about. They're talking about this. They're talking about Mighty Mouse's contrail. Okay, they turn that contrail into a physical object, just like you see there. Okay, and so what they're going to analyze is that contrail, and they're going to treat that contrail essentially as a physical object, because they say it's a trail of particles, for example, in a gas or a scratch in a metal, and that's what they're going to be analyzing. They're going to treat that as a particle that's scraped by. Okay, they're going to look at the tracks of that with this so-called cloud chamber. Okay, here's a couple of testimonies. These are modern-day testimonies of what Wilson did for science. He got his Nobel Prize in 1927 for his invention and development of the cloud chamber. And here's a couple prominent people in so-called mathematical physics that in Scotland, because Wilson was Scottish, and they analyzed what his contribution to science, to physics. Okay. And this is what they say. They say about Wilson, right? Wilson made possible the pioneering work for looking at the tracks of particles. Did he? I mean, are we looking at tracks of particles? Is that what we're staring at? Okay. A lot of particle physics discoveries in the 1930s and 40s and 50s were done with cloud chambers. Before him, there was nothing, nobody could actually track particles at all. Okay. But after him, says another fellow here, professor at University of Glasgow, says Wilson's cloud chamber, which he developed over almost 20 years, made things visible. Things visible? I don't know. All we see is a scratch, a trace. Is that a thing that's visible? Are we looking at a verb? Are we looking at a noun? What are we staring at when we look at one of those scratches or traces or whatever those are? Okay, so I don't know about making things visible. I wish he would have made the particle visible. Okay, and that's not the case. Whose properties had only previously been deduced indirectly. Well, we're still inferring all this indirectly. They're looking at a trace, what they think is a trace, and they're saying, look, that's a particle that zipped by. But that's an inference. All they're seeing is some kind of line there. What was the line made of? Was it, like I show in one of my pages in my website, if you skip a rope, okay, you're skipping a rope, and you hit it against the wall where there's paint, well, you're going to leave an arc. Well, that's different than saying that, you scraped an arc on the paint. Hitting it with a rope and marking it that way, like if you use a whip, and you whip the wall, and you give it a big slash, that's different than a little ball that's tracing and scraping the paint on the wall. Those are two different mechanisms. And so all they see is the trace. How can they tell from this line if that was made by a little ball that went across the wall, or was made by a rope that hit the paint in one go? How can they tell the difference? And they always consider only the particle. Now we're introducing an alternative for them to ponder. Okay. In a cloud chamber, they could actually see those things happening. Well, they could see it happening. They could not see things. Okay, so we got to distinguish things from happening. Happening is a verb, a phenomenon. Things are objects. We don't have to. We can't mix them. The things are the problem. We can't figure out what those things are. We can only see the happenings. Okay, we can see the effect. We can see what is visible. What is not visible is the mediator that caused that happening. Okay, so this is where this whole thing is leading to. This is where we have a problem with what we have today. They could check they were true and in due course when they discovered other sorts of particles. Again, they always thought of particles. Okay, they could inspect their properties visually. Again, they can't inspect the particle visually because they don't know if it's a particle. What they can inspect visually is the result, and the result doesn't tell us what caused that result, that phenomena. Okay, so I hope that you see the difference clearly there. Okay, black and white. Okay. Things didn't stop there. The particle, remember the particle notion of, especially of light, took hold starting the 20th century. The whole 19th century was a century essentially of waves, and that changed at the turn of the century, especially with these two gentlemen. One was Mr. Planck, okay, and he came up with the black body radiation, where he said, look, energy comes in discrete packages. And then Einstein, 5 years later, Planck did it in 1900. He got his Nobel in 1918 for that. Einstein did it in 1905. He explains the photoelectric effect. And essentially, he used Planck's quantum, the photon. That's going to come later, the name for it. But essentially, this is what becomes the photon. He says those discrete packages or packets of energy, those are what we call photons. And he was able to give a mathematical description to the photoelectric effect invented or discovered by Hertz, okay, in the 3 decades earlier. And for that, he received his Nobel in 1921, I think it was. Okay. Yeah, in fact, he received it 1 year before Niels Bohr got his. Niels got his in 1922, the year after. I guess they all said, look, if you give one to me, I'll give one to you. That's the way it was handled. Okay, the cloud chamber suffered some modifications over the years, and just like Wilson got his Nobel Prize in 1927, some Nobel Prizes were given also for development of the chambers, because it's not only detecting the particle, it's developing the technology that is going to help you detect the particle in the lab. And so those people, you know, the laboratory guys, the engineers who developed some of these gadgets to detect particles, they got their share of Nobels as well. And here's one. He's more or less an unsung hero. Nobody knows who he is. Where is he here? His name was Blackett. And he introduced a stiff spring. This is the modification he did to Wilson's cloud chamber. Stiff spring to expand and compress the chamber very rapidly, making the chamber sensitive to particles several times a second, and adding a film system to record images. In other words, by making it go fast, he was able to capture more particles that they could now see, or so they thought they saw. They saw the traces, and he put a camera in there, you know, to record. Essentially, what he did with next line there, he included a Geiger counter. Blackett also connected the cloud chamber to a Geiger counter, which detects the passage of a particle. In this way, a picture could be captured precisely when a particle passed. Okay, so they went into imaging. Okay, fast particles, or so they thought, and they could do imaging of those traces. Okay, he proved that at high energy, photons, right, produces pairs of electrons and positrons. Where did he get that? Well, he got that essentially from a couple mixtures. One was Carl Anderson, who's going to develop the positron, but the other one is from Dirac. Paul Dirac, he's the guy who proposed that there's a sea of particles out there in the vacuum, and this fellow is going to essentially confirm it by saying, look, with my chamber, now we can see more particle collisions, etc. And here we can see that some of these particles are coming in and annihilating. And so one is the positron, the other one is the electron. One has positive charge, the other one negative charge. They collide, they annihilate each other. So essentially this is what they were coming up with. This is the notion that was evolving from all this. Okay. I hope I'm still online. Let me know otherwise. Okay, here's another fella who also developed further, 1936. Name was Alex Langsdorf. He develops the diffusion cloud chamber. In other words, all these were developments of modification of the cloud chamber to get more precise images, especially, and more images as well. They wanted to see more and more particles whizzing by and particle collisions, and those are the ones they're going to study. Okay, so the diffusion chamber differs from Blackett's expansion cloud chamber in that it is continuously sensitized to radiation. So you don't have to wait for the particle to come. It's constantly flowing in there. Okay, to do so, it must be cooled to very low temperature. And there you see a model of the diffusion cloud chamber. Okay, so again, these are modifications to the cloud chamber. He didn't get a Nobel for that. He was part of the reason he's somewhat notable is that he was part of the Manhattan Project, the group that developed a nuclear bomb. Okay, And like he said, the first year they just had him working on his diffusion pump to improve it. Okay, but he never got a Nobel for that. Guy who did get a Nobel, however, was this guy, Cecil Powell. Okay, and what did he get a Nobel for? Well, there was more than just the cloud chamber. You had to also develop the photographic material. Okay, that's going to capture some of these images. Okay, and so he developed the photographic emulsion to facilitate the recording of the tracks of elementary particles. Okay, so that's what he gets his Nobel for. 1938, he applied his technique to the study of cosmic radiation at high altitude using specially designed balloons. So they were getting on top of mountains, they were flying balloons, they were doing all these kinds of things just to detect the cosmic particles, okay? And guess what? They finally discovered that you have all this radiation coming from outer space, from the sun, from the stars, you know, neutrinos, muons, pions, you know, they're all coming to Earth. We're bombarded with them every second. Maybe gravitons, Higgs particles, all this stuff was coming towards us. We were bombarded by all this stuff every second from every angle, okay? And so these people were trying to capture that invisible world, okay, with these chambers, okay? This work resulted in the discovery of Yukawa's Pion, okay? Remember Yukawa in 1935 proposed a meson, which is essentially a particle composed of two quarks, as eventually it came to be. At the time he didn't know that, okay, but he proposed mathematically to explain, you know, especially why the nucleus doesn't break apart, why the protons don't, you know, kick out another proton, essentially. And in other words, the integrity of the atom. That's one of the things he tried to explain there. And he created this so-called particle meson, which eventually is going to be identified with a particle made of two quarks, okay? So he gets a Nobel for developing the film, okay? And then a big one, right after the war, we have this fellow, his name, again, Nobel Prize. He develops the bubble chamber. So we went now from cloud, we go to bubble. Well, what's the difference? Well, reveals the traces of subatomic particles as trails of bubbles. You're going to put, well, let me read it. In a superheated liquid, usually liquid hydrogen, whereas particles collide with the metal in cloud chambers, particles have traces in the liquid hydrogen. So you put a liquid hydrogen inside a tank, and now you have these particles just whizzing through the tank. Okay, this tank is also, remember, you have magnets around this tank so that you can manipulate the particles. If they're positively charged, they go one way. If they're negatively charged, they go the other way. So they are able to manipulate these things with the magnets. Okay, that's essentially how an accelerator works. I work with accelerators known as implanters, and that's what they do. They have all these magnets on the outside, which, you know, not only squeeze the beam into a little pencil-like shape so that they can direct that. Okay. But on top of that, they can manipulate it and say, okay, I want the beam to go left or right. Well, all you have to do is play around with the magnets, okay? And what you do is, you know, like a television works with a raster, you know, just scanning the screen, okay? Okay, so he gets his Nobel for that, for developing the bubble chamber. Did we stop there? No, there was another development going on by other groups of people, okay? And they were working in parallel. Essentially, you had the imagers versus the counters versus the imagers. People who counted what they called particles, they were scintillations, essentially, you know, little sparks. And they were the sparks, the spark people, the people who counted using Geiger counters. And the other people who were interested in the images, in the traces themselves, and studied the traces, measured them, calculated their speeds, that sort of thing. So you had two groups of people. They were kind of rivals, and they didn't talk to each other much. It's like the string theorists and the quantum mechanics. You know, they don't talk to each other much. Each one does his own thing. Well, this is more or less the same thing. And the spark chambers were developed from the 1940s to the 60s, and they more or less started replacing even the bubble chambers eventually, okay, because they said, hey, you know, we can use these, especially after 64, they had the wire spark chambers. And, you know, these were developments, technological developments, to zero in more and more on, you know, on the particles. They try to figure out what particles are coming in, name them, measure them, calculate their masses, you know, their energies, this sort of thing. Okay, what is a spark chamber? It detects the presence of an ionizing particle by means of its ability to trigger electrical breakdown in a gas in a strong electric field. Key element is the Geiger counter that counted scintillations, you know, little flashes. So they're looking at the flashes, not really at the whole image of the trace. Okay, so that's why these guys were counters, the other guys were imagers. Okay, the goal was to build an improved timing device for detecting fast-moving particles, okay, without following a particle's trajectory, photographing sparks rather than follow particle contrails. And so there was a philosophical difference between these folks, and they developed different kinds of technologies, competing technologies. One time these guys were up, and the other time the other guys were up, and they all got Nobels for their efforts. Okay, computer technology replaces visual images. This is important because now we're going to make assumptions. Well, they were making assumptions already, but now we're going to let the computer make the assumption. And what are you going to feed into the computer? Well, you're going to feed a computer that what you're staring at are particles. So you're going to program the computer to detect any blip as a particle. I'd say that's where the danger comes in, because you've essentially certified and said, well, we've proven the particle, that's over and done with. Now we're just naming them and finding out, what they are and how much mass they have, how much energy, and what's their spin, and so on. So the particle is already not an assumption anymore. Now it's a proof. Now it's a fact. It's been over and done with. That's where the danger is. Now they're going to let the computers just read everything as particles, and this is blindsiding them to the possibility, to other possibilities. Like I say, did the mark on the paint on the wall, was that done with a little ball that went boom, 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 a little series of blips, or was it done in one whack with a jump rope or a whip? Those are two different mechanisms. And again, you have to consider all possibilities. These people never did. They always used the particle. Okay. Computer technology replaces visual images. Discharges detected as pulses. See, now they're going to look at these discharges. They're going to use the pulse or the blip, okay? And they're detected in wires. This came after 1964, I believe. Logged into a computer without intervening visual stage. So they're not interested in the visual part anymore. They're going to reconstruct it with a computer. Visual representations of interactions are reconstructed from computer data. The computer reads blips. The computer has an algorithm in there that's now going to manipulate these blips, particles, right? They're going to put them all together, and they say, okay, here's your trace. Okay, so the assumption is already long gone. The assumption is the particle. It's proof. It's fact. The computer is just going to be programmed to read every blip as a particle. Now they can reconstruct the traces, and now in the computer they can measure all that stuff and do whatever they want. They can calculate the mass, energy. Okay, so this is how these things were developing. Okay, and we moved on from that to even more. I guess you could call it. It's more technological development, but it removes the particle from the mind. In other words, you're farther and farther away from discovering that what you're looking at is not particles. Why? Because what they're doing is letting the computers do everything, and one of those is how to capture the particle itself. And what they're doing is they're using silicon chips now. You don't need all these big, gigantic bubble chambers. What you do is you let a silicon chip, capture that, okay? And so they went into this silicon detectors or semiconductor detectors, okay? Ionizing radiation is measured by the number of charge carriers, holes or electrons. Remember, a hole, when an electron leaves its valence band, goes into the conduction band, okay? In other words, it jumps from one atom to another, it leaves a hole behind. That's the way they look at this, okay? I know I studied device physics, which is a monster course, and they go through all this stuff where you have a negative electron, right? If you remove it, what you leave behind is a positive hole. Okay, and now as the electrons, flow of electrons is electricity. Okay, so you have the flow of electricity going that direction. That's the negative electricity, negative electrons. What is flowing in the other direction, in opposite direction, are the holes, positive holes. Okay, so you have a current of electrons and a current of holes. Okay, that's what they're referring to here. Okay, set free by radiation in the detector material, which is arranged between two electrodes. Okay, so what you're going to do is you're going to trigger all these electrons to flow. They're going to separate between electrons and holes. Okay, electrons and holes travel to the electrodes, resulting resulting pulse is measured electronically. Okay, so this is all done electronically now. No more going out there with a big batch of hydrogen and saying, okay, let's see what particle whizzes through the liquid. None of that anymore. That's too old-fashioned. That's 19th century. No, let's do 21st century. What they do is they put these electronic devices to detect and also to measure and amplify the signal as well. Okay, so it's all done electronically, and it's all done with computers. Keep that in mind. I'll show you why that's a problem. Okay, measuring number of electron-hole pairs allows the intensity of the incident radiation to be determined. Okay? And what's the advantage of this silicon detector? Well, compared with gaseous ionization detectors, density of a semiconductor detector is high. Okay, so the density is how you get to capture more particles to analyze. Okay, and hence charged particles can give off their energy in a chip, the silicon chip, of small dimensions. So you don't need these monstrous big cloud chambers anymore. Those are, you'll find them in a museum now. Okay, what is the problem with all this? I can give you an analogy, and it's got to do with what I used when I was in the industry, in the semiconductor industry, which were photomultipliers. Okay, so let's review very briefly what a photomultiplier is and why it's a problem. Okay, because they're making already a lot of assumptions, and which they call proofs, evidence, fact. Okay, here it is. Okay, if I can put it up here. Okay, here's a photomultiplier. Okay, and you can see more or less in the diagram up above what it is. You have a high energy photon, it comes into this region, okay, and it leaves an ionization tract. What comes out of there is, you have that scintillator, which is essentially a spark generator. Every blip is considered a spark, and they're going to sum or add or just trace all these, they're going to look at the lines left by all these traces, by all these so-called particles. The so-called photon, okay, we're going to assume the photon is a little particle. It's going to hit a screen, the photoelectron there that you see there at the interface. That's essentially the photoelectric effect, okay? Photons triggering the flow of electrons. And why is it called a multiplier? It's called a multiplier because they're going to amplify that signal. They're going to have this electron essentially hit more electrons or more atoms, and they're going to knock more electrons out of there. And from there, those electrons are going to cause more electrons to flow. In other words, it's a cascade. It's a, what do you call it? What's the term? It's used in the nuclear reactions where one thing triggers more and more to happen. I can't remember the term right now. Anyways, it creates these secondary electrons, and they're captured by the anode, and what you have is an amplified signal. You can see it starts out very light on the left there, and by the time it reaches the anode, you have that dark blue beam. And so that's how a photomultiplier works. It just keeps having all these secondary electrons being created by this constant chain. That's the term I needed. Chain reaction. Okay, so it creates this chain reaction. And on the bottom there, you can see, what's happening. More balls are being created as you go down the line, and you don't need to know exactly how many electrons you started out with. What you do is you do a calculation in retrospect. You just say, well, this is how much electricity was detected at the anode, and from that you have a calculation of of what came in. Okay, what came in is little, but what came out is big, and so you can analyze it. You can see it better. Okay, so what's happening? Well, the problem is it starts out with an assumption. They assume that the photon is a particle, and they assume or treat that the electron is a particle. And the problem there again is, if the electron is a particle, draw the atom for me. I want to see your atom. If you're going to treat the electron as a little bead that orbits the nucleus, what keeps the electron from falling into the nucleus? Because the nucleus is positively charged, the electron is negatively charged. Positive attracts negative. That little Earth should fall into the sun. Okay? And so again, you got to explain these things. And the other issue is, why doesn't the electron spontaneously fly out of the atom? Why doesn't the Earth fly out of the solar system? You got to explain this. Why doesn't it fall into the sun? Why doesn't it fly out of the solar system? And this is what they can't explain. And they leave that open-ended, like, don't ask that question. We don't know that. Because that's physics. See, they don't do physics. They do math. And they say, well, here it is. We got this little particle. It's got so much mass, so much spin. This is the energy at which it's flowing. Its velocity is near the velocity of light. They can calculate that as well. And just as important, they can calculate its lifetime, how long it lasts, okay, and they can measure that as well. Okay, let me show you that. Here you have the muon, okay, how they, when they detected the muon, we're going to look at these particle traces here. Okay, there it is, and you can see it cleaned out. And what they do is they look at, what it does, what reactions it does, how it moves. They calculate in this case, the 2.2 microseconds, that's how much the muon, that's its lifetime, and they can calculate the mass and the spin, okay. That's the muon. Here you have the pion, okay. Okay, this is another important particle they look at. Okay, here, let's clean it up. There it is. Okay, and you can see what happens. They look at how these particles collide. If there's a trace coming out of it, they say, or a couple of traces, like in this case, they say, well, it turned into these two particles. If they don't see a trace after a collision, they say it annihilated. Okay, this is what they do. They also calculate its lifetime there. Here's the neutrino. Okay, very simple. Okay, that's the original. Cleaned up, that's what it looks like. Okay. And yeah, this is what they do. This is what they spend their time doing with your tax dollars. They go in there and they look at these little lines, either through a gas or a liquid, like nitrogen, or really they use liquid hydrogen. Okay, in the case of bubble chambers, or in the case of cloud chambers, the old cloud chambers, they would just rip through the lead. Okay, so they only captured one particle, for example. Then they kept capturing more particles, and one of the trends in chamber developments to the one we have now with the silicon detectors is to capture more and more particles so that you can analyze. You have more material to analyze. Okay, so that's essentially where they're at. Okay, and so the problem is that this leads to, first to the particle assumption, then it leads to irrational explanations. Here's one irrational explanation. Okay, they assume that they're hitting something, a detector with particles. Okay, and what they do with the magnets there, you'll see two magnets now in a second, they are able to control in which direction, okay, the particle is going to go. Okay, and they can calculate different things through the radius of curvature. Okay, so this is what they do for a living. This is what they do. They simply assume that they're dealing with particles, and then they just measure things in there, and they say, well, this is so much energy, so much mass converted through E equals mc squared. Okay, this was the spin. This was how much lifetime that particle had until it annihilated itself, because they don't see a trace going all the way. They just see a little trace. It stops in the middle of nowhere and says, oh, it annihilated. Oh, why did it annihilate? Because I don't see anything going after that. Okay, and maybe, you did it with a whip. You did it with a rope. You hit the paint on the wall with it, and that's why that's why the mark ends there. There's nothing else, because that's where the rope hit. Maybe that's why they don't see, the trace continuing. You got to keep in mind these mechanisms, okay? And this is what they see, and this is what we propose they're staring at, okay? Here you see a particle collision, okay? This is what they simulate with their computers. Again, electronically. They already programmed into the computer that those blips, those pulses, are particles. And maybe what they're looking at is our atom. Our atom, when you smash, you're really either smashing particles, which I don't think is the case. I think what they have is two drill bits pointed at each other. And so it creates these sparks. And what it does is it sends the threads that make up the atoms in haywire, just go in different directions. And that's what those curlicues are that you see in all these images. What those are the threads going through gas, or through a liquid, or whatever environment you have. Okay. Yeah, here you have the irrational explanations. You can see here creation of particle pairs. Okay, positive and negative particles that are created. Okay, pair creation. They also have annihilation. When they don't see a trace coming out, they say, oh, it annihilated itself. That's how they determine that particles annihilate each other. They're antiparticles. Whatever an antiparticle is, why would an antiparticle turn a particle into nothing? And then what is nothing? See, because they say nothing is made out of something. Nothing is made out of particles. So what do you mean these two particles came together, particle and antiparticle? Okay, let's concede, black against white, positive against negative, whatever you want, I don't care. North against south, okay? So they hit each other and they turn into nothing. What do you mean it turned into nothing? Well, it turned into space, it turned into vacuum. What is the vacuum? It's made out of virtual particles, which can pop in through the void back at their discretion, right? Or at the mathematician's discretion whenever they want it. So if the space, if vacuum, if nothing is made out of particles, what do you mean by annihilation? What do you mean two particles annihilated? You mean they turned into space, which is particles? Particles turned into particles? What is this? So this is the issue, okay? Now you might say, well, Bill, we've seen traces. Okay, here let me show you a couple traces. This is uranium, okay? And you can see that something seems to be shooting out from ground zero, okay? And they call those alpha particles. In other words, those are helium atoms, and probably some beta particles as well, which are electrons, okay? This is what they think they're seeing there. And I have no problem with seeing this as alpha particles. I mean, I can imagine that an atom shoots out a subcomponent such as helium atom out of the uranium atom. That I can imagine. So I have no problem with that. That part I have no problem. That could be traces here, okay? Now let's continue. Here's another example, okay? And the question is whether here we're talking about traces. Again, it seems like they are traces. I could also think of this as whips, as again, ropes coming, not ropes, but threads really, coming in, moving the liquid around, Okay, so you can see this in any of those two ways. You can see those as particle traces coming out of the end of the needle, or you can see those as threads whizzing around and causing these motions in the liquid. And again, you can see some of those are somewhat curved. You don't see curlicues here, and that's something they have to explain. They just, more or less, what you see there are straight lines. And again, there is some curvature to those lines. Okay, again, could be whips. Okay, could be threads that are just coming up through the liquid there. And here it's even less noticeable. This is again uranium, but now you see like bubbling. No longer do you see like shooting out from ground zero. Okay, so you can see there's a little bit of difference in all these cases. And the question is, what are we staring at? What are those bubbles? What are those lines that we see? Are those traces, or are those whips or threads coming through the liquid? And here you can see some magnetic effects. Okay, I pulled out from the internet, and you can see there. You see what happens with liquid nitrogen. You see the rising bubbles in a magnetic field. It's a simulation there. You see this fellow there. He's attracting bubbles with a magnet. Okay, he blew some bubbles there, and he's attracting them with a magnet. And then the bottom right is also interesting. You have a sound field. Sound, how it affects a magnetic field. And when the thing is on the left there, you can see it's pushing all the bubbles up. Then suddenly it goes and there's a positive, so it turned the sound field off. Then it turns it back on. So you look at on, off, on. There's on. Here's off. Okay, and now back. Now you'll see on again. Okay, there you see on again. So you can do this, all these effects with magnets. And so the issue is whether a magnetic field, for example, is made of particles. What is a magnetic field? What caused all those effects? Was it a bunch of particles just whizzing by? Or is it something different? Like in the case of the rope model, what we say is those are threads that make up the magnetic field. Those are threads whizzing around. That's a different mechanism than saying you're shooting particles, discrete particles. And so again, all the technology for these chambers since the 19th century, all the way down to the 21st century, has always made the assumption, turned into proof, turned into fact, that what we're staring at are particles that are whizzing by. And so it's up to you to ponder whether that's what they're really doing, or consider an alternative. Are we talking about particles, or are we talking about threads? Okay. And so that's for you to ponder until next year. Okay. Meanwhile, oh, by the way, I just wanted to mention this again. Here you had one fellow also. His name was Tonomura, and he said that he handled one electron at a time to do the slit experiment. He created these fringes saying or thinking or believing that he handled one electron at a time. And again, we have to separate what he turned into proof, what he thought it was, which is simply an assumption. Okay. And these are two mechanisms. Their mechanism is the machine gun. They say they're shooting bullets. And what I'm saying is what they're doing is drilling those holes. And when you look at what's happening inside a chamber, what you're putting is two drills against each other, one running clockwise, the other one counterclockwise. And that's when the threads are whizzed all around, and those are the things that are going through the medium. And those are the lines that we see. So it's not that there is a particle whizzing creating the line. It's that you're whipping around the liquid medium and creating these lines that they later analyze and confuse with particles. And one of the things that you got to look at is, some of these annihilations, when the particle seems to go and stop in the middle of nowhere. Well, that does explain in great measure why the threads could be going through there, because the thread would just end there. Okay, whereas the particle should continue rolling. And so when they don't see the particle continuing, they say, oh, it annihilated itself. It turned into space. And what is space? Space is particles.